Okay, folks, you can hear me, right? Just checking again. Everything's good?
Yeah, we can hear you.
Okay. So let's see, it's like a minute before. I'll just write down what the plan is for today. Okay, so the plan for today is to continue our discussion of scattering in quantum mechanics. Hello? And the more specifically today, we'll be talking about, we'll continue our discussion of the Bourne approximation, and we'll start a new technique. We'll discuss a new way of thinking about it, which involves Green's functions, which is kind of cool. And so this is all about scattering. So we're talking about scattering now. So, okay, so let's sort of dive into it. Well, before we dive into it, let's sort of remind ourselves what's going on with scattering. So the idea is that for scattering, we have some potential like that. And for this class, it'll always be a central potential, like a Coulomb potential or screen Coulomb potential, some central potential. And we send particles at it, but they're quantum mechanical particles, so they're like waves with some initial momentum, and then they scatter, and they go into some direction. They get some new momentum, K final, and this angle is theta, and that's the scattering angle, and that's it. Folks, please mute yourself. Mute yourselves, please. I'm muting you guys now. I mean, you can unmute yourself to ask questions, but please mute yourself otherwise. Thank you. All right. So we have this scattering angle, and then there's some detector here. And that detector takes up some solid angle. Let's just say delta omega, the solid angle of the detector.
Professor, the detector is a ring-shaped detector, right?
Yeah.
Okay.
Yeah. It is. Although it doesn't have to be. I mean, you could actually break everything out in terms of theta and phi and just do that integral later, if you think about the math. But yeah, think of it as a ring-shaped detector, which is not unrealistic because, if you go to CERN, they actually have rooms where they have detectors, they'll have the interaction. Like if you go to a actual high energy facility, they'll have the interaction point where the beams collide, and then they'll have a sphere around it, and they will have detectors at every point on the sphere. So this is literally how they do it. Okay, I mean, so it's not just made up.
Thank you.
All right, and so okay, and so then the question is that we want to know is, I mean, the big question is, the big question that we want to answer is, what goes into the detector, basically, how much stuff goes into the detector. That's the question. In other words, what's the probability to scatter into the detector? That's the big quantum mechanical question that we're trying to answer with scattering. And so there's simple ways of thinking about, before diving into all the fancy math and stuff, there's some really just simple ideas that you should sort of get straight in your head, which I think are very helpful. And the simplest idea is that we have this, you can just think of, this is the simplest thing, is that we have some, think of there as being some luminosity going into the, going at this, at the potential, and that luminosity is the stream of particles. It's the number, this is classical thinking, but it's the number of particles per time per area. So it's purely classical. And then you can think of the, if you think of there being some little area here, this annulus that I drew last time of area d sigma, then the particles that go through that area are mapped into the detector. And so the number of particles that go into the detector is dn equals number of particles per time into detector, and then there's a mapping. And so you can think of all the particles that hit through that little area go into the detector. And so you will then have dn equals L d sigma. And I did this last time, but this is sort of my favorite way of looking at it. And so then you can say, well, that d sigma is not a very intuitive quantity, but what we can do is we can then divide by d omega and multiply by delta omega, which is the detector solid angle. And so now you see that the number of particles going into the detector is this. This is the number of particles per time into the detector. And then you can see that I know the luminosity, L, I know that because that's the particles I shoot at the potential. I know my detector because I built it painstakingly over a period of years and for a lot of money. And the only thing we don't know is this weird quantity, this ratio of d sigma over d omega. And so that's what we get using quantum mechanics. And so d sigma, d omega you get from quantum mechanics, the differential cross section. And you get this using quantum mechanics. And that's where all the quantum mechanics lives, in that thing. And so this thing is the most important thing, this d sigma d omega, even though it's this weird quantity. And you can think of it sort of intuitively as like, it's sort of basically telling you the probability to scatter into the angle theta, because that's what it's telling you right here from this little equation I just wrote. And so that's the most important thing. And so then we can see then that what is d sigma d omega? How do you get it? Well, I always like to start from this very simple equation, dn equals L d sigma, luminosity times area is number of particles per time. So then we can just invert this and say d sigma equals 1 over L dn, and then we can then divide by d sigma both sides of the equation. And so then we see that the differential cross section is equal to 1 over the luminosity times dn d omega. And this is purely classical, so it's really simple. But then what we do is to get for quantum mechanics, then all we do is we just replace particles with probability. And so then this tells us then that the d sigma d omega is equal to the luminosity now turns into probability flux. And that dn on the top turns into dr, d omega, where this is the probability per time that flows into the detector, flowing into the detector. That's what dr is. And so that's the quantum mechanical expression for the differential cross section that determines how particles scatter from a potential into some angle. And it's a function of the scattering angle. So then we calculated that last time, and we set it up, and then what we did was we to get the hard part is this dr, And to get that, we used Fermi's golden rule. That's what we did last time. And remember, we had this idea that we had this initial state, the momentum. That's the initial state that this went into Fermi's golden rule. And then we had all these possible final states because you can scatter into all these different directions. And so that's the density of final states, where these are the K final, all the possible final momenta, density of final states. But then we had to pick one direction because that's where our detector is, detector at scattering angle theta. And so we had to look at all the states going into the detector. And so the total density of states is rho of E, but then the ones going into the detector is d rho of E. So we had to pick a fraction of the density of states going into the detector. And from that, we set up our Fermi's golden rule, and I won't go through the math because we did it last time. But then what we did after going through all the Fermi's golden rule math, then we got the final answer, which is this, that the differential cross-section is a function of theta is equal to m squared over 4 pi squared h bar to the fourth, and then we have this matrix element E of r, and this matrix element is connecting the initial and final states, and that makes sense because the potential is the perturbation. It's sort of like we have an initial state, K initial, we have the potential, and then we have a final state, K final. And in the language of perturbation theory, the initial state is making transitions into the final state, and the perturbation is the potential. So it sort of it should sort of coincide with your intuition on perturbation theory. Okay, so this is what we got, and then just a little mathematical nuance is that for this expression, the state for this expression, to derive the expression, I put the universe in a box and I use normalized wave functions, but for the final expression, all the L's, the size of the universe canceled out. And so for this expression, the states are simple plane waves. And in other words, you can think of the universe as normalized to a size of 1 for this. And so if we look more closely, then what we see is that so now let's take a closer look at this expression. So obviously the most important part is this matrix element, because we just have some constants in front, and then we have this matrix element. So let's take a closer look at that matrix element, because that matrix element, all the physics of the scattering is in that matrix element. So let's take a closer look at the matrix element. And when we look at that matrix element, this is what we see. We can just write it out. We have a final state. We have the perturbation, which is the potential. And then we have our initial state. And so a matrix element is always an integral, so let's write out the integral. And so it's over all space. It's a spatial integral, and I have on the left, I have my final state, complex conjugated, my final momentum, I have my potential, and then I have my initial momentum. And this is what determines scattering. And now we're going to analyze this little integral a little bit further, but before diving into the math, I just want to say that we are about to derive conservation of momentum in quantum mechanics. So listen closely. This is conservation of momentum in quantum mechanics, and this is the closest you will ever get, in my opinion, to conservation of momentum. It's living in this matrix element that you're staring at right now. And so let's try to understand what it means to conserve momentum in quantum mechanics. It's not the same as classical mechanics. So let's think about it. So let's take a look at this integral, because conservation of momentum is hiding in that integral. And so let's rewrite it. And we can have e to the minus I kf minus k initial dot r, and this is v of r, the potential overall, integrated overall space. So this matrix element, this is the matrix element that's determining the probability to scatter it to a particular angle. And so let's take a look at this, because what's happening is this is a really interesting matrix element, because I can think of k, I have this thing here, kf minus ki, which is the transferred momentum, I'll call it q, is equal to the transferred momentum. So that's the momentum transferred to the particle. And that's, I think, not a hard thing to see, because it's just the final momentum, you know, and by the way, you know, P is equal to H bar K. So when people talk about K, we often just refer to the K as momentum, even though momentum is actually H bar K. So we see that this Q is the final momentum minus the initial momentum. So that's the momentum transferred to the particle by what? What gives the particle that momentum? Now I'm asking you a question. What's the answer?
The potential?
Yeah, of course. There's nothing else there. Exactly. The potential is giving that momentum to the particle. But what does it mean for the potential to give momentum to the particle? Because the potential is just sitting there. It's not like a car, you know, moving and two cars go bang. You know, it's not like that. The potential is just sitting there. So how does it give momentum to the particle? Well, we're about to see that. Because what happens is, if we look at this, this integral, it's e to the minus I q dot r times v of r. Now, here's the thing about these integrals. You guys have seen these integrals before. If you have an integral, this is like a basic thing about integrals. If we integrate a wiggly thing over all space, what does it equal? Integrals of wiggly things equal what? Tell me.
0?
Yes. That's sort of a general concept. Now, there's some nuances to it, you know, and I don't want to get into all the mathematical nuances, but you guys have to. You're undergraduate students, so go for it. You know, do all the mathematical nuances. But, you know, 30 years later, the only thing you can remember is integral of a wiggly thing is 0, okay? And that's the most important concept. And so that means that this integral is 0, right? Because I got this wiggly thing. That is a wiggly thing because it's a wave, right? Waves are wiggly. So integrals of wiggly things are 0. So this integral wants to be 0. But how can it not be 0? This is how it cannot be 0. The only way it cannot be 0 is if somehow the wiggly things cancel and the integrand stops being wiggly, okay? So how can it stop being wiggly? Well, this is how. E to the negative I q dot r, and now that potential, let's do a Fourier transform. Let's do a Fourier decomposition of the potential, and I'm just going to do it as a sum. It's actually an integral, but whatever. The point is the same. So that potential, I can write as a sum over all possible momenta. It's I'm doing a Fourier transform now. E to the I q dot r v of q. So now I'm breaking apart that potential into all of its Fourier components. Fourier components. Okay, and I have to give it a different, I got to give it a q prime because I'm already using q. Okay, so I've broken that potential into all its Fourier components. And so now I've turned this integral into a million integrals, you know, over all the different Fourier components. Each one is being integrated in that integral. And here's the point. Every one of those integrals is 0 because it's an integral of a wiggly thing, except for one little piece of that of all these integrals. Because look, this thing is equal to, it's a sum. I can pull the sum out, q prime v of q prime. Let's just write it out. so it's more obvious. And then this becomes an integral of e to the minus I q dot r e to the I q prime dot r d cubed r. Okay, so now I'm basically integrating this Fourier component of the transferred momentum with all the Fourier components of the. I'm integrating the transferred momentum over all the Fourier components of the potential, and it all goes to zero because this is wiggly, right? Except it's not wiggly for one special situation. What is that situation? Tell me.
Q equal to Q prime.
Say it again.
Q equal to Q prime.
Yes, yes, that's right. It's wiggly except for Q prime equals Q. That's right. That's right. The integral is zero except for that one component. And that one component means that all of these integrals are zero. So that means it equals zero except for Q prime equals Q. And so that means that this thing is going to be equal to, see, they all go to zero, but then it's just, this whole thing is going to collapse to this V of Q prime. So that's the matrix element. That's what we calculated. You see, it's the Fourier transform, and that's sort of an obvious thing, you know, when you look at the math, because you know we're calculating this matrix element, but this matrix element is just a Fourier transform of the potential, and so so from a mathematical point of view, it's very trivial. It's just a Fourier transform, but from the physics intuition, the idea is that the this matrix element, all the components of it equals zero, except for the one component where the potential is providing the momentum that goes to the particle. And so that's the way to think about it. You can think about this as this is the Fourier component of the potential. And so, oops, this Q prime wasn't there. I made a mistake. Let me get this right. And so the point is that the potential is providing the momentum. The potential provides it, and the potential provides it because the potential has a Fourier component at precisely that momentum. And so the potential has to provide the momentum because the potential has its own wave component at exactly that same wiggly wavelength, because that's how you should think of it. The potential is formed, has all these wiggly components, as Fourier components, and one of those components matches the transferred momentum, and so that's the component that gives it the momentum, and this is the strength. This is the strength of the potential's component of potential at Q. And so the strength of that Fourier component in the potential tells us how strong the scattering is. So it all kind of works out. It's like, and so if the potential does not have a Fourier component at the transferred momentum wave vector, if the Fourier component is zero, there is no scattering. So the transferred momentum is provided by the potential, and here you can see it in the equations. So I know it's like a bunch of equations, but there's an intuition there. It's conservation momentum, and that's as close as you're going to ever get to conservation momentum. That in quantum mechanics, that is the essence of conservation momentum in quantum mechanics. So hopefully that made some sense, or if not, think about it. Okay, so then we see that. So then we get this very simple thing, which is that we see that the differential cross-section in the Bourne approximation, which tells us the probability to scatter into some angle, is simply proportional to the Fourier component of, I'll call it V of Q squared. And sometimes people put a little wiggly, I didn't really do that. Yeah, I'm just gonna leave it like that. So this is the Fourier transform squared. So where Q is the transferred momentum. Q is equal to K final minus K initial is equal to the transferred momentum. And I will just make one other comment, which is that this is equivalent to the theory of diffraction. This is really the theory of diffraction, because if you can think of, if you know anything about diffraction, and you might not, because I don't know if you've seen it before, but diffraction is when you have a diffraction grating, right? You have a periodic structure and you're throwing a wave up against a periodic structure and it bounces into some direction. And there are special directions that you get because of the constructive interference. And so the idea is that the potential is a diffraction grid. So actually the potential is like a series of diffraction grids. You can think of every Fourier component of the potential is a diffraction grid. And so one of those diffraction grids is exactly the right one to bounce it into that final momentum. And that is the Fourier component, that is the diffraction grid that gives it exactly the right momentum to go into that direction. It's not analogous, it is literally exactly the theory of diffraction. So that's another thing to think about. It's quite cute. Okay, and so then, okay, so let's do an example now. So here's an example. Let's consider the Yukawa potential. Let's do scattering off of a Yukawa potential. Scattering off a Yukawa potential. Now, this stuff was all invented by high energy experimentalists and high energy theorists, but I'm a condensed matter experimentalist. So when I also think about scattering a lot, but when I think of it more in the context of solid state physics. So that's the language that I prefer to use. So for me, this is all happening inside of a crystal, but it's the same thing. That's the beauty of it. The physics of scattering inside of a crystal is the same as the physics of scattering, at CERN, in Geneva, in one of those big giant high energy colliders. It's all the same. So let's consider a Yukawa potential. And so the idea of a Yukawa potential, this is the idea is like, suppose I have like a crystal. So since I'm a solid state physics guy, let's consider crystal silicon. And then let's put an impurity in there. Like, let's say phosphorus, a phosphorus atom. So let's put a phosphorus atom in there. And then let's shoot electrons at it. How do I shoot electrons at it? Well, I just have an electrical device and I pass current through it. It's the same thing. It's the same physics. So if I have a little silicon device with a single impurity, and I'm just flowing current in it in a nano device in my computer, that's the same thing as a scattering experiment at CERN, same physics. So I'm shooting waves at it. I'm passing electrons into it with some incident probability flux. And I want to know how many of them go into this direction where I have, say, some other electrical circuit or transistor or something in some funny direction in this direction, which is some angle theta. And so this is like a real question, a real problem that people actually think about. And you could use this to design some little electrical circuit. So I want to know, what is the probability for the electron to hit that impurity atom in my electrical device and go at a particular angle? So that's like an actual question that you might really worry about. And so I want to know how many electrons go into that angle. And so I know that, well, I know that from the little equation we did before, dn, the number of electrons per time that go into that angle, is going to be d sigma d omega times, let's see, or I have my 1 over j. I'm trying to remember the little formulas. I have 1 over j times the solid angle of the detector. So that's how many of them. So I need to know the incident current. I need to know the size of my detector, and then I need to know d sigma d omega. And this is what I get using quantum mechanics. So this tells me the number of electrons per time that go into my detector, number of electrons per time. And so all I need to know is d sigma d omega. D sigma d omega equals what? Okay, well, I have this charged atom, and so the question then becomes, well, I know how to figure out d sigma d omega because I now have the Bourne approximation, which we just derived, and I know it's some formula. Where's the formula? There it is. It's going to be m squared, the mass squared, over 4 pi squared h bar to the 4th times this matrix element, the initial momentum connecting to the final momentum squared. Okay, so that's my differential cross section. And so the question then is, what is V? Okay, so I have a charged impurity, so somebody tell me, what is V? What is V?
You said it's charged, so is it the Coulombic potential?
That's exactly right. And so V, let's just call it 1 over R. Let's forget about well, let's see, let's call it V naught, a constant times 1 over R to keep the units right. That's right, it's V naught over R. That's right, the Coulomb potential. Now, the Coulomb potential, it turns out, is actually sort of hard to deal with. It's a hard potential mathematically when you go through all the math. But it turns out that the Coulomb potential is actually not very common. And so the actual potential that those electrons see is not the Coulomb potential. Can someone tell me why?
There are other electrons that are attracted to there, so it's neutral.
Yeah, and there's a word for that. Do you know what the word is? It might not be exactly neutral, but there's a word we use because the other electrons might not perfectly cancel it, but they might partially. It could depends, on the details. What's that process called? Does
Like
anybody know?
electronic dipole or something?
Yes, the dipoles do it. If it's a metal, the electrons do it. If it's a insulator, the dipoles do it. But there's a word for it. What is it? What are they doing? The verb. They are blanking. What are they doing?
Is it screening, Professor?
Yes, screening. That's right. Exactly. It's screened. And because of the screening, then the potential that the electrons see is not the Coulomb potential, it's the screened Coulomb potential. And I'm not going to derive what the screened Coulomb potential is. That's something that you do in like physics 110, 110A, or maybe physics 141A, I forget. One of those classes you do it, you derive it. I'm not going to derive it, but I just want to motivate this discussion to tell you that if you were to derive it, if you were to like take a Coulomb potential and then screen it in a material, then you're going to get a screened potential. And the screen potential is what? I take the Coulomb potential and I multiply it by what? Does anybody know? Does anybody know? Okay, so I guess none of you have seen it. I mean, that makes sense, because you'll see it later on. It's it gets screened by an exponential, and that's it. And R is equal to the screening length. And so it turns out that the Yukawa potential, and that's called the Yukawa potential. And it turns out that this potential is actually more common than the Coulomb potential. You would have never guessed that. And the reason is because screening is always happening. So in materials, there's always some level of screening. And so the Yukawa potential so a Coulomb potential really is always screened. So instead of Coulomb potentials, really what we have are Yukawa potentials. But remember that if R goes to infinity, then your Yukawa potential turns into a Coulomb potential. So sometimes the screening length is really long, and so you think you have a Coulomb potential because you can't, because the screening length is like, 100 miles big or something, but really you always have a Yukawa potential. Okay, so now I'm scattering across this Yukawa potential, and I want to know what is this differential cross section for scattering off a Yukawa potential, because I want to know what happens when my electrons are going through the silicon device and bounce off of this phosphorus atom. So I know the potential is a Yukawa potential, and the screening length is just the screening length of silicon is some number that you look up in a book. And so now let's calculate this differential cross section. And so I got to do, and so to calculate the differential cross section, what I got to do is I got to calculate this matrix element. This is the most important thing. And so I'm going to call this write it like this, VFI. So that's the matrix element that connects the initial state to the final state. Matrix element. So I got to calculate this. And so it looks like this. It's going to be an integral over all space of e to the minus I kf minus k initial dot r of my potential, which is v naught e to the negative r over big R, the screening length, divided by little r, d cubed r. And basically, this is just the Fourier transform of the Yukawa potential, right? This is just the Fourier transform of the Yukawa potential. Because I just want to know what is the strength of the Yukawa potential for what is the Fourier component strength at the transferred momentum wave vector. That's the whole point, to conserve momentum. Okay, so I got to do this integral. And it turns out that this is a slightly hard integral. But it's not so hard that you can't do it. It turns out that it's a famous integral, and famous integrals are ones where some smart person has figured out a trick, okay? So this is a famous integral. It pops up in physics every now and then, and so people have figured out how to solve this integral. And so there's a mathematical trick for solving this integral. So I'm going to show you the trick. So this is the trick. What we do is you have to set up, there's a famous way to set it up, famous geometry. So let's set up the scattering geometry. So this is the geometry. We have the initial momentum, and we have then the final momentum, okay? And then we have the angle between them, which is the scattering angle. And then here, I connect this. That is going to be my transferred momentum, K final minus K initial. Okay, so I think that this can kind of make sense. And so the trick is this. This is the trick. The trick is to do this. Draw a little line there, and then do a little just do a little trigonometry. Notice that we have the right angles there, and this part right here is ki sine theta over 2. Okay, so do you see that? That's just a little bit of trigonometry. So where theta, because I've just divided that triangle in half. And so then what I can do then is I can then from this triangle, I can say that the length of this side is kf minus ki. The length of that divided by 2 is equal to ki sine theta over 2. All right, and then we can do something else, because remember that energy is equal to p squared over 2m, where p is equal to h bar k, and so energy is equal to h bar. Just sort of reminding you this little formula, h bar squared k squared over 2m, And so from that, I see that K is equal to square root of 2 ME over H bar. So, so I always use this little formula, but I just want you guys to remember where it comes from. And so then we see that because of conservation of energy, then we see that what is the relationship between K initial and K final? Are they related? Tell me. Are they?
Yeah, they are the same.
Exactly. They have to be the same. And the magnitude of them both is this. It's just that little formula I wrote. Square root of 2ME over H bar. So whenever somebody said, and so what I'm going to do is I'm just going to call this parameter K, all right? Instead of Ki and K final, it's just K, because it's the same. It's a length of a wave vector, and it's square root of 2ME over H bar. Okay, and so then what I can do from this, I can say that the length of K final minus K initial is equal to 2K sine theta over 2. All right, so this is just a cute little geometrical fact where theta here is equal to the scattering angle. Okay, so that's some pretty simple geometry actually. But now comes the trick for the integral. The big trick is this. The big trick to solve the integral is to pick the z-axis to be proportional to the direction kf minus ki. And that is not obvious. I mean, if you've never seen this trick before and someone said solve this integral, you probably wouldn't have picked that. It's a very clever trick, sort of obvious in hindsight. So pick the z-axis to be in that direction, and then solve your integral. And so so then what we have is now we can solve the integral in spherical coordinates. And we have we have this direction, which is the direction of kf minus ki in that direction. And so now we're doing the integral, and we're solving the integral. We have this vector r prime, and that's the integrating variable. I forget the words that you use in math, but it's the variable you're integrating over. We're integrating over r prime. And so then I have this angle, which is theta prime, not the scattering angle, it's the integrating angle. And then I'm also going to be, have this angle, phi prime. Okay, and then this length is r prime. So I'm integrating over this variable r prime, and my z-axis is in the direction of kf minus ki. Okay, and so then we can now set up my and so this is the integral. I have it written up there. So VFI is equal to this integral e to the minus I kf minus ki dot r. Let's call this r prime times times v naught over r prime e to the negative r prime over r. I get all these things. Yeah. Okay. Good. So this is my integral, and so now I'm going to use our tricks now, because now this dot product can now be equal to the length of kf minus ki times the length of r prime times the cosine of the angle between them, which is now cosine theta prime, using this construction. And so this integral now becomes this. It becomes, I'm going to take out the v naught, and it now becomes a triple integral from 0 to 2 pi, 0 to pi, 0 to infinity of e to the negative I 2k sine theta over 2 times r prime cosine theta prime times e to the negative r prime over r prime times r prime squared dr prime sine theta prime d theta prime d phi prime. Okay, that's the trick. And it's I mean it's actually pretty simple. If you're getting lost in the math, then don't worry, go home and do it, and you'll see that it's quite straightforward. It's just a bunch of little steps. But the thing to remember is that this theta prime is the integrating variable, and this theta is the scattering angle. So you got to keep it all straight. And now once you've set the integral up like that, then it becomes really simple, because you can then separate the angle. Everything separates really nice. I'm not going to do all the details, but I'll do a few details to get this. The r prime, the radial part becomes simple. R prime e to the negative r prime over big R, and then the angular part. The phi part is trivial. That just turns into 2 pi. The theta part is still kind of hard. You know, for the theta part, you have this e to the negative 2i k sine theta over 2 times r prime cos theta prime sine theta prime d theta prime. But now you do a change of variables, and then it becomes easy. So now you say u is equal to cos theta prime, and so then du is equal to negative sine theta prime d theta prime. And now you can see that everything becomes simple, because now this integral becomes 2 pi v naught 0 to infinity dr prime r prime e to negative r prime over r times negative 1 to 1 e to the negative 2ik sine theta over 2 times r prime u du. And that's actually an easy integral. And so it's a lot of steps, but this is just that's just a simple exponent, a simple exponential. So you can do that integral easily. That's easy. So we've reduced this really hard integral to actually very easy integral. And this is also an exponential integral, so that one's easy too. Okay, so I'm not going to take any more steps of that, but what's going to happen then is you're going to see that after you do all of the, then if you take the absolute magnitude of that, then you're going to get this in the end. The absolute magnitude, because that's the only part that matters, is going to be 4 pi v naught r squared times 1 over 1 plus 4 k squared r squared sine squared theta over 2. Okay, so that's the answer. That's the matrix element connecting the initial and final states. And then when we plug it into the Bourne, then we just plug it into the little Bourne approximation formula, which just has a couple, we square it and have a couple of constants in front of it. And so then we get the d sigma, d omega, the probability basically to scatter to some angle theta is going to be equal to m squared over 4 pi squared h bar to the 4th times dfi squared And so then that's going to be 2mv naught big R squared, the screening length, divided by h bar squared, squared times 1 over 1 plus 4k squared r squared sine squared theta over 2 sine squared theta over 2 quantity squared. Okay, that's it. So we got it. We got the differential cross section for the Yukawa potential. That's going to tells me how the particle bounces off the scatter into some angle, which is actually a very useful quantity. And so now, what do we do with it? Well, let's take a look at this differential cross section. Let's go a little further, and then because this is the way you should be thinking about it. This is the process that this formula is telling us. It's like I have some initial momentum. I have my potential, which is a Yukawa potential, and then I want to know my probability to scatter into some final momentum, K final, and then this angle is theta. So that's the whole process. And so now let's consider what happens in some limits. Let's take some limits. Let's consider first the low energy limit. And the low energy limit means that the energy goes to 0. But if the energy goes to 0, remember, K is equal to square root of 2me over h bar. And so in the limit that the energy goes to 0, what does K do? K goes to what?
0.
Right. And that's the same as the wavelength does what? What is the wavelength doing? K, low energy limit means that the wavelength is doing what?
It gets really long.
Exactly. So this is the long wavelength limit, or the low energy limit. It's the same thing. So the low energy limit means that K goes to 0, same as saying that the wavelength goes to infinity. And so then let's look at our little formula, and we see that d sigma d omega of theta is what? Look at the formula above. What is it? What kind of function does it turn into? Can anyone tell me?
Does the second part goes to 1, so it's just the first part squared?
And the first part, what kind of function is that? Do we know all those parameters? Are they all known parameters in the first part?
Constant.
What?
It's constant.
That's right, exactly. Good, that's exactly right. So it all goes to a constant because we know all those parameters. And so now this is actually an interesting result. It's not obvious because basically this is saying then that d sigma d omega as a function of theta, and remember theta only goes from 0 to pi because pi is backscattering. So you can't scatter more than pi, right? So pi is the biggest theta can get. And so it's saying that d sigma d omega is constant. And so what that means is that it means this. It means I have a scatterer and I'm sending my wave at it. That's my plane wave. And now it means that I have the same probability to scatter into every direction. It's isotropic. So it means that it means that my scattering is isotropic. So it's isotropic scattering, isotropic. And we just did a bunch of math, and so it's hard to sort of see the intuition, but I just want you to sort of appreciate that this is very strange. It's very non-classical behavior. Because if I have a BB, if I have a potential and I shoot a classical BB at it, the probability that the BB does not have equal probability to scatter into every direction. That's nonsense. That's crazy. That makes no sense from a classical perspective. But it does make sense from a wave perspective. If you guys know anything about diffraction, then you know and you might not, and so I don't want to, I'm not criticizing you if you don't know this, but I'm just saying, you know, for when you learn diffraction, this is something to look forward to, is if you have an object and you send long wavelength waves at an object, then those long wavelength waves wrap around the object and then go out. So they sort of like, that's diffraction, long, and you guys have seen this a little bit, you know, long wavelength waves wrap around objects and then go spraying out into all directions. That's a property of diffraction. So classically it makes no sense, but from a wave diffraction perspective, it makes perfect sense. And of course it makes sense because the quantum mechanical theory of scattering is exactly this theory of diffraction. It's just waves diffracting. Okay, so it's like diffraction. So that's kind of cute. So this is consistent with diffraction, but it's very non-classical. Because we do have particles, and like the particles are literally flying in all directions. So that's kind of cool. We get isotropic scattering. But now let's consider the high energy limit. High energy limit. And the high energy limit, of course, is now there's the formula, is now k goes to infinity. And so now you see that basically what's going to happen is that the d sigma d omega is now going to be proportional to 1 over sine squared theta over 2 when you look at that formula. And so now when I plot it, d sigma d omega from 0 to pi, it's highly peaked where? Where is it big? Tell me, I'm asking you a question. Where is the d sigma d omega big? At what theta?
Like 0 and pi and 2 pi. Oh, no, 2 pi.
Yeah, 2 pi. But 2 pi we don't go to, we only go to pi, right? Because pi is as big as we get. So it's highly peaked at 0. So it looks like this. It's highly peaked and then it goes down. You know, it's just some function. But it's peaked at theta equals 0. And that makes sense, because what does it mean to be peaked at 0? It means that I have a potential and I shoot my wave at it, high energy wave, short wavelength, k initial, and it tells me that the highest probability is that my particle goes in the theta equals 0 direction, which is this, k final. That's theta equals 0, which means no deflection. And that makes a lot of sense, because if I have a high energy particle and I have this potential, it's like the high energy particle doesn't even notice the potential, it just goes blasting past it. It's like a bump in the road, you know? It's like I got a little, it's like I'm driving a Mack truck and there's a mouse in the road and my Mack truck is going 100 miles an hour and I run over the mouse. Do I notice it? Yes or no? I don't. I just run over that mouse. I don't even know it's there. And that's what's happening here. It's just a Mack truck running over a mouse. Boom. I'm sorry for that analogy if you don't like it, but that's kind of what's happening. Okay. So now let's consider the total cross section. And so the total cross section is going to be, it's basically the area that corresponds, remember, you know, I'm scattering into 4 pi, and so I want to know what angle, what area of the beam is deflected into 4 pi. So area of beam deflected into 4 pi. 4 pi, all 4 pi of solid angle, the sphere. And so we can calculate that pretty easily, because it's just going to be sigma is equal to the all solid angle all solid angle, sigma d omega, where d omega is sine theta, d theta, d phi, right? That's d omega. And so we do that, and so I'm not going to do the integral, but when you do it, then when you do the integral, you see that you get an answer, and it's going to be 2mv0 r squared over h bar squared times 4 pi over 1 plus 4k squared r squared. And you can see then that for low energy, where k goes to 0, then you can see that sigma is equal to a constant, which is equal to, you can think of it like this, pi times some r squared, pi r squared, where r, the radius is some, when you do the math, you can see that the radius is going to be 2mv0 r squared over h bar squared, just when you do the math. So so the the total cross section corresponds to some area where the radius has some effective radius, where it's this thing when you do the math. And then for high energy, when k goes to infinity, the cross section is what? What's the cross section? Tell me. Can you see? It's this formula right here. What's the high energy cross section?
0.
Yes, exactly. Because it's like, because as I said before, the particle has so much energy that when it hits that potential, it doesn't even notice. It just goes blasting past it. So, okay. All right. So that was a fairly detailed Bourne approximation problem. And so you can see that the Bourne approximation is very nice. It let us solve that problem in great detail. We got a lot of physical insight from, we got all these formulas, and we see all these detailed physics of the scattering. So Bourne approximation is really nice. We all love it. Bourne approximation is very nice. We get a lot of insight. It helps us to understand scattering a lot. And so the Bourne approximation is the simplest way to understand scattering. And the Bourne approximation is, I'll just say it again, it's the differential cross section is proportional to this, basically the Fourier transform of the potential. That's the major insight. It's that. Okay, so that's basically the Bourne approximation. But now let's realize that it doesn't always work. Doesn't always work. And so now we have to go beyond the Bourne approximation. But first, before going on beyond the Bourne approximation, which is a lot of math, it requires Green's functions and all this stuff. Before going beyond the Bourne approximation, let's understand, like, why do we have to go beyond the Bourne approximation? So let's consider a simple problem. Let's consider hardball scattering. Hardball scattering. And hardball scattering is that our potential V of R is equal to a constant for our no, I'm sorry, it's the idea of a hard ball is that the potential is infinity for R less than or equal to R naught, and it equals 0 for R greater than R naught. And so that basically is a hard ball. So that means I have a ball with some radius, R naught, and I'm shooting a wave at it. I'm shooting my particles at it, K incident. And I want to know, and I want to ask the question, what is the probability that I go into some detector here at some angle theta? Okay. where that's my K final. Okay, so suppose I give you a hard ball and I say, what happens when I scatter a particle off of a hard ball? And that should be like a really easy problem, because you guys remember, like in normal quantum mechanics, when you had like a particle in a box, you put the walls to infinity, everything becomes easy because you guys know that the boundary condition, when the potential goes to infinity, what is the wave function at that point in space? I'm asking you a question.
Should be 0.
Right. So you guys should sort of vaguely remember that when you have hard walls, quantum mechanics tends to become easy because the boundary conditions are very simple and well defined. You don't have to like match the boundary conditions, you know, like you don't have to say, oh, the wave function on the right is equal to the wave function on the left and the slopes are equal and it's such a pain in the ass. Instead, you just say the wave function is 0. Boom. It's really simple. So we like that. So this should be a very simple problem. So the question is, what is the scattering? You know, what is the probability that I scatter my particle into some angle theta? Okay. So what happens? So let's try to solve it. So the first thing we do is we say, let's use the Bourne approximation. And so when we do it, we say, okay, we got to calculate this matrix element. So I got to take this, I got to do this integral. I have e to the negative I k final minus k initial, the transferred momentum, and I got to find the Fourier component of the potential, right? I got to do that. So I got to calculate this matrix element, that I'm going to square it, and that's going to give me my differential cross section. But now comes a problem, because this is an integral over all space. And so what happens when I do this integral? Because I have now my integral has two regions. I have the interior region, r less than r naught, and then I have the exterior region, r greater than r naught. So what does my integral equal when I do the exterior region? Tell me. What am I going to get when I try to integrate the potential in that exterior region?
0.
Yeah. What am I going to get when I do the integral in the interior region?
Infinity.
Right. Is that good or bad?
Bad.
Bad. It's a bad thing. That's right. It's bad. Because now the integral equals 0 in this region, and here the integral equals infinity in this region, and basically that's just telling us that it's all screwed up. It's messed up. It's not well defined. It goes to infinity. It's all screwed up. Okay, and so this is telling us that the Bourne approximation fails. Bourne approximation fails. But I just want to say that this is a very physical situation. This notion of having a hard ball scatterer where a quantum particle bounces off of a very hard potential, it happens all the time in real life. It's a very physical situation. And so this is a problem. You know, this is a very simple physical situation, and the theoretical treatment that we have developed fails. All right. And so that means that our theory wasn't good enough because we're missing some important physics. And so I'll tell you why it fails. The reason it fails, because the Bourne approximation came from perturbation theory. We use Fermi's golden rule. And you might have forgotten all the details of Fermi's golden rule and what goes into perturbation theory, but there is an important component of perturbation theory, which is that the perturbation is what? Strong or weak? Strong or weak? Tell me.
Weak.
Yeah, weak. Perturbation theory works for weak scatterers, but now we have a strong scatterer. So the hard ball is a strong scatterer. And so it makes sense that the perturbation theory treatment, which was developed for a weak scatterer, doesn't work. So for the perturbation theory to work, the scatterer has to be kind of weak. And so this is what's happening in the Bourne approximation. I have a scatterer, V of R, and I have my initial state, which is e to the I ki dot r. It's an incident wave, right? And then I have my final state, which is some wave going in the final direction, k final. And it's going in this direction, and I have this angle theta. And so this is a plane wave. My final state is a plane wave, and my incident state is a plane wave. And so basically I have one plane wave going like that, transitioning into another plane wave going like that. That's what I meant to draw. You see what I'm saying? Where this is the angle theta between them. That's what the Bourne approximation is telling us. Go from plane wave state, and then we have transitions to boom, another plane wave state. And in this case, that fails. So why does it fail? Well, I told you, the perturbation theory only works for weak potentials, but also I want you to see intuitively why it fails. The reason it's failing is because the states are not plane waves. Because what's happening is the wave function has to go to 0 at the location of that ball, the hard ball. And so that means that the wave function is highly altered in the vicinity of the ball because the wave function goes to 0. It's not a plane wave anymore. And so the approximation that our initial and final states are plane waves is garbage. And that's why it failed. The states are not plane waves. So the Bourne approximation is great if you can make the approximation that the initial and final states are plane waves. But sometimes you cannot make that approximation. Sometimes the actual states are very different from plane waves. And so that's what we have to take into account. And that's what we're going to do now. And so, the states are not plane waves. So what happens when the states are not plane waves, which is actually the more general case. So what we need is a more general theory of scattering that takes this into account. More general theory of scattering, which takes into, we need a more general theory of scattering, which takes into account the fact, that the states are not always plane waves. And this new theory of scattering is the Green's function. We're going to use the Green's function approach. Green's function approach. And the Green's function approach is kind of simple. I mean, it's a different way of looking at the scattering problem. It's actually a more general, it's a better way. But better often means, more mathematical, more sophisticated. So here's the Green's function approach. Let's do this. Let's consider that we have some weird potential. I'm trying to motivate the Green's function approach. Let's suppose that we have some weird potential. This is my potential, V of R. Okay, suppose it has some weird shape and some weird arbitrary potential. And then what I'm going to do is I want to shoot a particle at it. And basically what I can do is I can solve the Schrodinger equation. If I solve the Schrodinger equation, I can solve, what we do is we solve the Schrodinger equation to get the wave function at all points in space for E greater than 0. because remember, scattering is all about the positive energy wave functions. So I know that if I go far away, then it's sort of like a plane wave. I can have some incoming wave. But then as I get close to this weird potential, my wave fronts are going to start getting distorted. You see, and it's going to start looking more like a plane wave as I get farther away. But you see how this is what the solution to my my Schrodinger equation is. There's shape to it, right? Because it's diffraction. My wave function like wraps around that potential and scatters off of it, and I get all these weird shapes and stuff and weird interferences. And so what I can do then is if I actually, so the more correct thing to do is to actually solve the Schrodinger equation for this weird potential. And if I solve the Schrodinger equation, so if I can actually calculate the real wave function, and remember the Schrodinger equation is just H psi equals E psi, right? So if I can solve the Schrodinger equation, and H is really simple because H is just kinetic energy plus potential energy, where the kinetic energy is just, negative h bar squared over 2m del squared, right? You know it. So if I actually solve the Schrodinger equation for this weirdly shaped potential, I'm going to get some wave function, psi of E. Now, if I want to know how much particles are moving in all different directions, like let's say now I put my detector here. There's my detector, and my detector covers some solid angle, d omega, just like before. But now I want to know how many particles go into my detector. How do I figure it out? I want to know how many particles go into my detector. And I have the wave function, and I want to know how many go into the detector. How do I figure it out? You know, can you tell me the answer? I got the wave function. I want to know how many particles are flying into my detector. Does anyone have any clue how I can figure that out? Tell me.
Would you integrate the wave function squared like over the area of the detector?
That's a really good answer. I like that a lot. You're really thinking. That's not exactly the right answer, but that's pretty close. That's very good, because you're trying to take a physical quantity that is associated with the wave function and integrating over the detector. So that what you said was quite smart, because psi star psi is the probability of finding a particle in space. And so then you integrate it over the detector. That's pretty smart. That's pretty good. But it's not quite right. And the reason it's not right is because this is a time-dependent process. What we want is dn. Remember, if the number of particles per time. But in quantum mechanics, it's not dn, it's dr, which is the probability per time. So what you just told me was the probability, psi star psi. But what I want is the probability flow. I want to know how much, because the probability is like water, it's moving. I want to know how much of that water is flowing into the detector. So you almost got it. So you said integrate psi star psi against the detector, and that was almost right. Instead, I want to integrate something else. What else? Tell me.
The probability current then?
Yes, exactly. That's exactly right. The probability current, that's exactly what I want. I want to know the probability current. And the probability current is going to be J. And so suppose I have a small detector, dr is going to be Je dot what? I integrate its flux. So I got the probability flux. I integrate it over what? What do you integrate flux over to get the stuff? How much stuff?
Maybe the solid angle times the rate.
It will be the area.
Oh yeah.
It's an
Radius.
area.
Okay, yeah.
Yeah, okay, and you've all done this. I mean, I know you all know this. Okay, so the amount of stuff per time, if I have flux hitting some surface, the amount of stuff going through the surface is the dot product of the flux dotted into the area vector, where that ds is, you know, that's like a little vector that's perpendicular to the surface. You've all done this before. Okay, so that's what I need to do. And JE, of course, is a vector, and that's just my h bar over 2mi, you know, psi star del psi minus psi del psi star thing. Okay, so what? So here that's the point. The point is that if I have the wave function, then I can calculate the probability current, and if I have the probability current, then I know everything. So the wave function tells me everything, because now what I can do is I can say, remember, I can say that, you guys remember that, you know, the differential conductivity, I'm sorry, the differential cross section is 1 over J incident times dr over d sigma. And so what that means then is that using this definition, the J incident is just the value of J far away, way over there to the left. So I just calculate the J incident is way over here on the left. So if I know the wave function, I just go far, far away and calculate J, and that's my J incident. D sigma d omega equals 1 over J incident. And then if I want to know what goes into my detector, I just have to calculate my J dot ds of my detector divided by d omega of my detector. And so this then is the differential cross section. Okay, so that is a more exact expression. There's more physics in this expression than there was in the last one. So this is the proper way to do it. But this way is harder. This is a harder way. It's better, but it's harder because to do it this way, you must actually solve the Schrodinger equation, H psi equals E psi. And for the last one, we did not solve the Schrodinger equation, because remember, perturbation theory, the whole point of perturbation theory is to not solve the Schrodinger equation. That's why it was invented. So, you know, so the other way we did not solve the Schrodinger equation, but for some situations you have to. For some situations, the perturbation theory fails. And so that's what we're going to talk about now. And of course, I don't have time to do it all, and so I won't, but I just want to set it up for next time, because what we're going to do is we have to solve the Schrodinger equation. And then once we solve the Schrodinger equation, we get psi. And once we have psi, then we get J. And once we have J, then we get the differential cross section, because the differential cross section is just going to be 1 over J incident times J dotted into my detector divided by the solid angle of my detector. These things, remember, these things are connected. They're not independent. The ds is the area of the detector, and the d omega is the solid angle of the detector. And so that's what we have to do next. And so what we're going to do is, next what we're going to do is we're going to solve the Schrodinger equation to get the wave function to get J. But we're going to solve it for E greater than 0. So we're solving the Schrodinger equation in a regime where you don't have as much experience, the positive energy regime. And to solve the Schrodinger equation, what we're going to do next time is we're going to use the Green's function approach. And that's what the whole point is. The Green's function approach is just a way to solve the Schrodinger equation. You use it to solve the Schrodinger equation. Okay, that's it. So I got to stop now. Folks, I cannot go to office hours today because we have a special, we have incoming graduate students or graduate students who are potential graduate students who are looking at graduate schools. So we have a special function for the physics department today at 11:15 a.m. that I have to go to because of the visiting graduate students who are visiting by Zoom. So I have to go to that. So I can't go to my office hour today. I'm sorry. So I'll catch you next time. Okay. Bye-bye.